Hi friends, today we're going to talk about part 1 of Module 11, inverse functions. The first thing we want to talk about when we talk about inverse functions is, we need to be able to determine if they're one-to-one. And so one-to-one is kind of the opposite of a function. When we say for a function, the definition of a function, and we learned this earlier in the semester, is that for each x, there exists exactly and only one y. A y can have more than one x, but each x can only have one y. Well, for something to be one-to-one, we flip that a little bit and we say that each y value is associated with only one x value. And when we talk about defining whether or not something is a function, we say that it needs to pass the vertical line test. However, in order to determine if something is one-to-one, it would pass the horizontal line test. All right, and then a function that's always increasing or always decreasing is definitely going to always be a one-to-one function. So we have a picture here, and we'll think about this. Do each of these represent one-to-one functions? So the first one, no matter where I draw a horizontal line, it's only possible for that horizontal line to cross the graph once. So in this case, we would say yes, it's one-to-one. However, the next one, if I drew a horizontal line, it would cross in two spots, not one-to-one. So if we look at our third picture here, I could draw a horizontal line here, only crosses once, draw it here, only crosses once. What happens if I draw it on the x-axis? So does it cross only once, or does it cross twice? So this point right here at 1, 0 is not defined. So drawing a line through there is not touching the graph. All right, so in this case, it's only touching at one spot. So this would be yes, it is one-to-one. And then furthermore, if we look at this last one here, if I were to draw a horizontal line at y equals -1, it would cross at two spots, and so we would say no. So visually, that's really all we need to know to determine if a function is one-to-one or a graph. All right, so the horizontal line test is what we use. And the reason it's important for us to determine if something is one-to-one, because one-to-oneness would indicate that the inverse, which we're going to talk about in a second, is also going to be a function. So here we have two conceptual pictures, and we want to determine if each of these are one-to-one. In order for us to do that, you need to remember that each y has only one corresponding x, only one x. So this y value corresponds back to two x's. We would say no. But in the second case, each of those goes to their own y, so we can say yes. All right? So one-to-oneness is defined by each x having only one y, just as a function is defined as each y having only one x. So moving on to inverse functions. If a function is one-to-one, then it has an inverse, which would also be a function. Now, there are situations sometimes where things are not one-to-one, and we can create a restriction, and we'll look at an example like that later. So if it's not one-to-one, we can restrict it. An example might be if we had a parabola opening up, that's not one-to-one. But if I said, well, we're only dealing with x values that are greater than or equal to 0, we might be considering just the right half of a parabola. And so that's what I'm talking about when we say restrict the domain. We create a restriction so that we can do the problem. The most important thing to remember about finding inverse functions is that you interchange your x and y values. So when I say inverse, in your mind you want to think we need to switch x and y. Okay? Further, the domain of a function is the range of the inverse, and the range of a function is the domain of the inverse. So I like to think about it like we have a domain of f and a range of f. And what's happening is those domains and range are switching places. So the domain becomes the range of f inverse. We use that -1 for notation there. And the range becomes the domain of f inverse. So when we do these problems and we talk about finding domain and range, all you're going to need to do is find the original domain and range of the given function and then interchange them or switch them. The domain will become the range and the range will become the domain of both the inverse functions. All right, so here we have an example. We're asked to find f inverse of the function. So thinking about what we've just talked about, an inverse, and this -1, I didn't address that up above, the -1 is notation for inverse, all right? So we don't read that as f -1 of x, that's f inverse of x. And if you've ever done math, maybe some linear algebra or used matrices, when we want to talk about an inverse matrix, we put that -1 there. Or in trigonometry, when we talk about inverse trig functions, we use a -1 to indicate that we're talking about an inverse. So we want to find f inverse of x. And in order for us to do that, we're just going to interchange my x and y values. So this first ordered pair would become -2, 1. The second one is -5, 3. The next one we've got 0, 4. And my last ordered pair here is 8, 6. So in order to find the inverse, all we're doing is switching the x and y value. So part B here says f inverse of -5. Well, in the inverse function, when x is -5, my output value is 3. So 3 would be my answer there. So we have one last example. We're given the graph of a function and we would like to graph the inverse. So in this case, our original function, f of x, has several ordered pairs marked on the graph. We have -4, -2, -3, 1, -1, 2, and 1, 4. So my inverse, which I'm going to indicate as f inverse of x, use that -1. My inverse is going to be the ordered pairs -2, -4, 1, -3, 2, -1, and 4, 1. So all I did was switch all my x and y values. So if I plot -2, -4, 1, -3, 2, -1, and 4, +1, I get a graph that looks like this. So this red graph that I've just drawn on the page represents the graph of the inverse function. Okay? And what you want to notice about these two, the original and the inverse function, is that they are a reflection over the line, which is called the identity. And that's always going to be the case. the graph of a function and its inverse are always going to reflect across the identity and make this mirror image.